Well, hello and welcome to the Education Center at Harbor Branch. As you can see from the title slide, the topic today is climate change, just an introduction to climate change. The topic is really very broad. We can think of it in terms of causes and effects. We will be emphasizing the causes today. There are only 10 of them, 10 possible causes, and maybe a few of those aren't especially important. There are many effects, and there are too many to cover, so I'll be looking at just one of them, sea level change. That's probably the most important effect for those of us in Florida, because we're surrounded on three sides by ocean. I want to make the point throughout the talk that there are both natural and anthropogenic causes of climate change. If anthropogenic is not part of your working vocabulary, I'll just mention here and probably repeat later on that anthropogenic deals with human activity. So if any climate change is due to what you and I are doing, that would be an anthropogenic cause of climate change. I'll have those color-coded as we go through the slides, and I will remember to point out which of the causes we can influence and which we have no control over. I might mention also that we'll be working with a wide range of time scales. Climate changes as short as seasonally. If we go, for example, from a summer to a winter season, from a wet season to a dry season, time scale here would be on the order of months. On the other hand, some of the climate change mechanisms here will be occurring over millions of years. So we have a wide range of timescales to work with. I think I mentioned that there are both natural and anthropogenic causes. We can divide the causes into two different categories. One is extraterrestrial, things going on out in space, and I'll start with that. And then terrestrial, and by that, that will be generally covering processes that are going on in the ocean, over the earth, on hard ground, solid ground, and then in the atmosphere. And as I mentioned, the only effect we'll be working with is the rise and fall in sea level. I'll give you some examples from geologic times in the past, tell you what's going on now, and then we'll look at the estimates for how sea level will continue to rise over, let's say, the next several decades. I want to make the distinction between climate and weather. I will be talking about climate. I have included weather, but I've grayed it out here so we see it, but that's just to remind me that the emphasis will definitely not be on weather. But just in passing, weather is what you observe when you look out the window on a given day. It's what's happening right now. But if you take today's weather and add to it last year's weather on this day, the year before that on the same day, and so far and so forth back as far as you have information, and you average all of those days of weather, anytime you hear the word average, you know we're talking about climate. So the average is probably the best measure of what you would expect on this day. But of course, a particular day can be unusually warm, deviate from the climate that way, or it can be unusually wet or dry or cool. So there can be deviations about the average, but the average is the climate, and that's what we will be talking about today. Climate is usually characterized in terms of temperature and precipitation. These are the two main climate variables. Temperature, for example, can vary widely from the equatorial, tropical, warm, humid climates to the polar climates. There can be a change with latitude. Also, at any given location, oftentimes there will be a change over the course of a year. So you go from a distinct winter season to a distinct summer season. Similarly, precipitation can vary. The two extremes would be rainforest with very heavy rains. At the other extreme would be the desert. And like temperature, rainfall, precipitation can vary over the over the course of a year. We have distinct wet and dry seasons here in Florida. But there are other ways we will not have time to touch on today. But if a place has unusually strong winds or unusually clear or cloudy skies, that might be important enough to include in a description of the climate. So there are other possibilities for describing climate, but in the interest of time, we will restrict the talk today to just temperature and precipitation. Climate can change in either of two ways, and I have grayed out the one over on the left. Climate can change from place to place. As I mentioned, there can be tropical climates and polar climates, so climate definitely changes with latitude. As we see from the picture here, which was probably taken at a low elevation in subtropical area because of the palm tree, we can see the climate can change with elevation. Certainly the climate where the picture was taken with the palm tree would be distinctly different from the climate at a higher elevation on the mountain with snow and ice. Down at the bottom below the picture, I make the point that we're going to ignore this and focus on the other possibility. Climate can change from one time to the next. Now, I've already mentioned it can change over the course of a year, but it can change also over the much longer time scales. Over almost any time scale, it can go from cooler to warmer or warmer to cooler. You can see the arrow there is pointing in both directions. Similarly, for precipitation, it can go from drier to wetter or wetter to drier. And this is the climate change that we're going to be talking about, climate change over time. I mentioned in the first slide, I believe, that this climate change can be natural. It's been happening for millions of years before humans came along. I will color code that green. You'll see that a lot. It can also be anthropogenic, that is involving human activity, and I'll color code that red. And I believe I mentioned the time scales vary widely. This figure is going to be very useful for providing the structure or the framework for everything that I have to say. These are the 10 causes of climate change. You can see they're in two general categories. Along the top with the black background, the extraterrestrial factors, those that are happening outside the Earth's atmosphere in space. And then around the bottom with the blue background are the terrestrial or the oceanic or the atmospheric climate change processes. And I'm going to start at the top with solar output, go through those quickly, and then make a loop around the bottom, a counterclockwise loop starting with volcanic emissions. I will have this slide on the screen from time to time just to remind you of how we're structuring this and where we are in the talk. So we're going to begin with solar output. And in fact, some of the global warming that we have been observing in the past maybe 50 or 100 years is due to the fact that the sun is burning just a little bit hotter. We've had measurements perhaps over the last 140 years. There's not complete agreement on just how important solar output is in explaining the warming. One group, I think it's the government, a governmental agency, is saying it could be explaining up to 10% of the observed warming. There's a school in California that's saying that it might be as much as 25%. Regardless of the exact number, that will probably be pinned down a little bit better in the coming years. But regardless of the exact number, it is playing a role and has to be factored in or has to be included with the other primary causes. If you look at the figure, the red curve on top is showing the temperature change since the 1880s, and the blue curve then is the solar output, insolation, incoming solar radiation. I think, yes, I have that down at the bottom of the slide. Insolation is not the insulation that you have in the attic. In this case, insolation with an S-O-L is an abbreviation for incoming solar radiation. It includes the ultraviolet, it includes the visible sunshine that we would expect, and it includes infrared radiation. We do get infrared radiation from the sun. Anyway, the bottom curve is the insolation, incoming solar radiation. And if you divide the curve in two parts at about 1960 or so, you see there's a general relationship, a little bit ragged, but there is a general relationship between the two from the start of the record on up to about 1960. They're both climbing irregularly, but they're both climbing. But then they seem to diverge. The solar output levels off and might even be decreasing at the very end, but the temperature continues to rise. So if there's a cause and effect relationship, it seems to have been better in the early days than it is right now. The temperature is rising, but it doesn't seem to be a result of solar output. So there have to be other processes going on, and we will be talking about those in the coming slides. Earth-Sun geometry is the second of the extraterrestrial factors. If you think that the Earth just goes around the sun in a circular orbit, that is not the case. We deviate from that. We have an elliptical orbit around the sun. Then just the degree of how non-circular the orbit is the eccentricity. Sometimes we're further from the sun, sometimes we're closer to the sun. And as you might expect, when we're closer to the sun, solar heating is going to be a little bit stronger. Further away, it'll be a little bit weaker, and so the eccentricity will explain small part of climate change. The tilt of the axis, that's understandable. I don't know if the word obliquity is in your vocabulary, but it's just the tilt of the axis. And that will determine if the sun is apparently more overhead or less overhead. If we're tilted, if one hemisphere is tilted toward the sun, the heating will be a little bit stronger because the sun will appear to be just a little higher above the horizon. So that would affect climate change. Precession, that one is a little tougher to describe, so I put the top animation in here. And the axis of rotation of the top is about like the axis of rotation of the Earth. And just as the top starts to wobble just before it falls over, I guess, the Earth's axis of rotation will wobble also. It will trace out a cone shape. And again, this sometimes has us pointing more toward the sun in the northern hemisphere, and that would increase our heating. Sometimes it has wobbled over halfway around, a complete wobble, and it is pointing away from the sun, so the heating would be more intense in the southern hemisphere, less intense up here. So as the wobble continues, one after the other, our heating will be more or less intense, and that explains part of the warming and the cooling, the coming and the going of the glaciers. Altogether, over geological time, the effect can be calculated, and it has been found that these variations in Earth's orbit going around the sun, the Earth-Sun geometry can explain as much as 25% of the climate change. Before man came along and introduced the anthropogenic causes of climate change, this is pretty much all that was going on. Solar output and this Earth-Sun geometry, the Earth-Sun geometry mechanisms. And these explain natural climate change quite well. I think the third item in the extraterrestrial factors is interstellar dust. This is probably one that could be excluded. It has an effect, but relative to the others, it would appear to be very, very small. But any dust in space between the sun and the Earth would tend to scatter incoming solar radiation, and insolation that is scattered then does not get through to the Earth, where it can be converted into heat and provide warming. These particles of interstellar dust are quite small. One has been magnified and photographed here, and this particular one, which I assume is representative, is about 14 micrometers. Now, a micrometer, as you can see over on the, or at the bottom of the slide, is a millionth of a meter. We're talking about something very small. If you compare it with an average grain of sand, which might be on the order of 1 millimeter, a micrometer would be 1/1000th the size of a grain of sand. So this one, it's 14, but let's just call it 10 micrometers. This would be about 1/100th, 1% of the size of a typical grain of sand. Now, I include this as a possible cause, I guess partly just so I can include this next figure taken from the Hubble telescope. This is a picture of the Iris Nebula, kind of picture we could get only from Hubble, taken outside of the atmosphere because the atmosphere just makes this too hard to see. The Iris Nebula is 1,300 light years away. A light year is a distance. It's how far light travels in a year, which is about 9.5 trillion kilometers. Just for 1 year, we've got 1,300 light years. So the whole thing, multiply the two, and you get 7.64 quadrillion kilometers. Now, my point here is that if we can see something, if Hubble can see something that is 7.64 quadrillion kilometers away, there can't be a lot of space dust between Iris and Earth blocking the view. So if there's not a lot of space dust to block the view, there's probably not a lot of space dust that would be changing climate either. But we'll include it anyway. Now, you can see from the insert in the upper right part of the figure, we've covered the extraterrestrial factors, solar output, which is increasing, Earth-Sun geometry, probably the most important of the three, and now interstellar dust, certainly the least important of these three, and maybe the least important of all 10. We move to the terrestrial, oceanic, and atmospheric causes of climate change. And just following along in the figure, I'm going to begin with the volcanic emissions. The example that I'm giving here, one that's documented quite well, is the eruption of Mount Pinatubo in the Philippines in 1991. The graph in the lower left shows you that Earth's surface temperature was increasing irregularly up to that point. You can see from the vertical line where or when Mount Pinatubo erupted, and certainly at that time there is a distinct shift from irregular warming to irregular cooling. The total amount of cooling before it looks like it was starting back up was only 0.7 of a degree centigrade. That might not seem like very much, but in the realm of climate change, 0.7 of a degree is actually quite a big deal. Effects are temporary. From the peak of that curve in June or July of 1991 to the bottom, it looks like it was about a half a year or so. I think actually that might be more like 1 year, from about the middle of 1991 to the middle of 1992. But that's how long it took for the dust to fall out of the atmosphere, either just under the influence of gravity, or maybe it got rained on and taken out that way. I have forgotten to call attention to the natural or anthropogenic process line on each of these slides, but as you can see from the bottom line here and on all of the previous slides, we've been talking about natural processes. Mountain building. Now, if volcanic emissions produce effects over on the order of a year, very quick in climatological terms, mountain building is producing changes relatively slowly. This is at the other extreme. I'm using the term millennia here, which means thousands of years. I can't find a word like millennia that refers to millions of years. If there were that term, I would be using it. This is something that is occurring over tens of millions of years. Mountains do not build quickly. The process for mountain building is when two continental plates come together, and you recall plate tectonics from an earlier lecture that I gave you. When these two come together in the horizontal, the only way to go is up, and a mountain can be slowly built in that way. The Himalayas are a good example of that. As the mountain builds, depending on the wind conditions, there might be winds up one slope of the mountain and down the other. If there's moisture, as there usually is in that air, as the air rises, it expands. As it expands, it cools. As it cools, the moisture condenses and precipitates, and that rainfall is called orographic precipitation. Now again, orographic may not be in your vocabulary, so I defined it down at the bottom of the slide. Orographic just means relating to mountains. Just as the moisture in the air, or some large fraction of it, gets rained out on the way up the mountain on the upwind side, that air then is drier, correspondingly drier on the downwind side. And so as the process continues, then the dry air coming down the opposite side will produce what is called a rain shadow. We have orographic precipitation on the upwind side, rain shadow on the downwind side, and as the mountain continues to build, there should be more and more orographic precipitation, and the rain shadow should be more and more pronounced. This, of course, is also a natural process. We have no control over mountain building. This next slide is entitled Continental Drift. We know from the earthquakes and tsunami talk that the appropriate term is plate tectonics. This refers to the movement of crustal plates across the surface of the earth, and the crustal plates can be both oceanic crustal plates and continental crustal plates. So I prefer plate tectonics, but the term continental drift is the one that is on the slide we are using, so I have used that here as well. The idea here is that if a plate moves from one latitude to another, and I'll be using the one that you see highlighted in each of these four figures, as it moves from one location to the next, if that movement is a change in latitude, you would expect that the climate would change correspondingly. In the upper left map, you can see the circle over a plate that is going to become India. It looks like it is at mid-latitudes in the southern hemisphere, so we would expect that the climate at that time would be the climate you would expect at that location, which would be a mid-latitude, maybe with distinct seasons. That was 200 million years ago. Moving clockwise, which would be horizontal to the right, we get the next snapshot of Earth's continents. This was 130 million years ago. 70 million years later, we can see that the plate has moved equatorward. It's probably now subtropical, maybe not quite tropical, at least part of it is subtropical, and the climate would have changed correspondingly. In the lower right figure, we can see now part of that crustal plate has crossed the equator, and this, at least that part of it, would definitely have a tropical climate. And then finally in the lower left, we see India. Now it's India, it's in its proper place. It has moved into the Asian continent, and by the way, there was significant mountain building associated with that. That's how we got the Himalaya mountains when India joined Asia and the two plates came together. The only way for the Earth's crust to respond would be to rise up, and it did so big time, producing the Himalayan mountains. Again, this is occurring over millennia, many millennia, so as to include time scales on the order of tens of millions of years, maybe even hundreds of millions of years, and it's a natural process. Next on the list is the atmosphere-ocean heat exchange. The idea here is that water, ocean water, can soak up heat at low latitudes in the tropics, And then if that water gets caught up in an ocean current, which moves it poleward, that heat can be released to the atmosphere at some higher latitude, and it can affect the climate of the surrounding area. The example that I'm using here is the Gulf Stream. This is color-coded. Right along the coast of Florida, you can see it's a very dark red. This indicates very warm water. And as it moves northward in an irregular sort of a pattern, we lose the dark red, but we still have red. And then finally that gives way to the yellow and the green. That just means that this water is cooling. It is giving up its heat to the surrounding water areas or atmospheric areas, continents, whatever. The climate at these higher latitudes would be warmed by the heat that is given up by the Gulf Stream. Again, it's a natural process. We have no control over that, but it is affecting climate at these, even as the Gulf Stream exports heat from the tropics, keeping that just a bit cooler perhaps. It is importing heat to higher latitudes, warming the climate there. Surface reflectivity. This occurs in a variety of forms. The one that I'm going to touch on here is the surface reflectivity, or the change in surface reflectivity that occurs when ice melts into water. This would be a high latitude process. This is getting in the news quite a bit. We are losing Arctic ice. The procedure here is that the climate warms a little bit and it starts to melt the ice. As the ice melts, what had been an ice-covered area now becomes a water-covered area. The reflectivity of ice is very high, maybe 90% or even 95% of the insulation that comes in and hits ice or snow is reflected back into space, reflected back up through the atmosphere anyway, and perhaps out into space. And so that insulation, that reflected insulation, is not available for heating. On the other hand, as the ice cover is reduced and is replaced by water, you can see from the dotted arrow that is shown on the figure, some of this insulation penetrates into the ocean. It's converted into heat. The rest would be reflected, but that which is converted into heat would tend to warm the ocean, which melts even more ice, which exposes even more ocean, which absorbs even more sunlight. So there's a feedback process going on here. And once the ice starts to melt, by whatever reason, the process tends to continue. And that's what's going on in the Arctic right now. It's losing substantial amounts of ice just from the changes in surface reflectivity. And as the ice is replaced by water, the climate is warming. It's an important climate change mechanism up there. This next slide shows one more version of reflectivity. This is reflectivity that's going on in the atmosphere rather than at the surface. This one involves clouds, and you see a cumulonimbus cloud over on the right in the figure. And I've got a hatched line indicating incoming solar radiation coming in, hitting the cloud top, and then reflecting back into space. This is not a perfect reflection. Some insulation does get through the cloud, but a large part of it will be reflected, it does not get through to the surface, and therefore will not be available for heating. This process is kind of like the reflection that occurs off the volcanic ash, the reflection that occurs off the ice. The greater the amount of cloud cover, the greater the reflection, and the greater the cooling effect on the climate of the Earth's surface below. One version of cloud top reflection, and this I think is the first time we see anthropogenic color-coded, contrails, which are condensation trails produced by commercial aircraft or military aircraft, Condensation trails under the right atmospheric conditions can persist and they can expand, and we are seeing in the upper left part of the picture, we can see some condensation trails that persisted and have expanded into significant cloud cover. These are thin clouds, but they have the same effect of natural clouds. There is reflection off the top, and that blocks some fraction of the light that would have gotten to the surface and been converted into heat. This is anthropogenic because they can be traced back to airplanes, and as airplane traffic increases under the right atmospheric conditions, the contrail effect can increase also. Next to finally, for the atmospheric reflectivity, I want to talk about haze. This is also anthropogenic. This one is a little more complex because there can be two possible results from haze that's put into the atmosphere, let's say by factories, as you see in the lower right figure. If the haze absorbs incoming solar radiation, the haze particles, the little particulates, will warm, and so the effect will be a heating effect. On the other hand, if rather than be absorbed, the insulation is scattered back up, that will reduce the amount of insulation that gets to the surface, and so that will have the same cooling effect that we saw in the case of clouds or volcanic ash. Now, there may be haze resulting from, let's say, pollen from trees. That can have a hazy effect. I think the Blue Ridge Mountains are called Blue Ridge Mountains because at certain times of year, the pollen creates a bluish haze. That would not be anthropogenic, but for the most part, factories are producing the haze, and that is definitely anthropogenic. Related to this, and this is the final reflectivity slide, related to this is the climate change that comes from atmospheric dust. In our case, in Florida, we have a special version of that. The haze originates on the African continent, which is, I believe, about 4,000 miles away across the tropical North Atlantic. It's carried out onto the Atlantic and in some cases all the way across to us by the trade winds. The trade winds are strongest in the summer and perhaps early fall. I've got June to October listed on the slide. An example of that is in the lower right here on the screen. I happened to be offshore in July of 1982 with my camera, and that was a very dusty day. It's about as dusty as I have seen it. Normally, even for a setting sun, it's not a good idea to look directly into the sun, but in this case, we could do that, and I could even take a picture as the sun set. This was African dust. In spite of all of the dust that I'm sure fell out of the atmosphere during the 4,000-mile trip from Africa to Florida, in spite of all of that loss of dust, we still had this much influencing the picture that I took. This is probably a natural process. The dust storms are certainly natural, but there may be poor agricultural practices where exposed soil is contributing to the dust. So there may be an anthropogenic component to this, but I'm thinking that this is mostly natural. That's the only cause I'm going to put on the slide. The last topic in the causes of climate change is atmospheric chemistry. And I think I have to take one step back here, give you some background in the form of the greenhouse effect. If you have been in greenhouses on a cool day when they've got the windows closed, then you know exactly what I'm talking about. Even if you haven't been in a greenhouse on a cool day, you've probably been in a car that had the windows rolled up on an August or July afternoon. And you know when you get back in that car after 15 minutes, half an hour or so, you know how hot it can be in the car. Same thing is happening in the greenhouse as is happening in the car. So we could call this the parked car effect, I guess. But in the case of the greenhouse, the walls might not be transparent, but they're certainly translucent. They let a certain amount of insulation come in, and what insulation, incoming solar radiation, does get through the walls of the greenhouse will tend to warm the air inside, but then that covering on the greenhouse prevents that warm air from escaping. So the inside of the greenhouse stays considerably warmer, and you can extend the growing season in the greenhouse beyond what it would be just outside. In the case of the atmosphere, the analogy is not quite perfect. We don't have walls on the atmosphere, but most of the process is the same, which I think justifies the use of the term greenhouse effect for what's going on in the atmosphere. Some people will refer to this as the atmospheric effect, which is probably a better term. Here, as in the case of the greenhouse, we have insulation coming in. And the atmosphere will screen some of that, some of the infrared, ultraviolet, visible light. Not all of it reaches the surface. That would be like the translucent walls of the greenhouse. But a lot of it, half or maybe a little more than half of the insulation gets to the surface. It heats the surface, and as the surface heated, it starts to radiate back out into space. But this is long-wave radiation. And long-wave radiation does not get through the atmosphere going out as easily as the insulation got through the atmosphere coming in. There you can see a little bubble or a cloud-like icon that represents carbon dioxide. In the middle, just off to the right of the middle, is water vapor, and there is one that you might not recognize, CH sub 4, that's methane. These are three very important greenhouse gases. They're important greenhouse gases because they absorb the long-wave radiation that is going out from the surface. As they absorb it, they heat up, and so they then radiate. Some of that radiation is going upward and is, in fact, lost to space, but some of it comes back downward, and it's this return of long-wave radiation from the greenhouse gases that help insulate the Earth. There are 6 greenhouse gases, some less important, some more important. Over on the far left is water vapor. That explains about half of this greenhouse or atmospheric effect that we have on Earth. That's an important one. Carbon dioxide, I have encircled that because I want to come back to that. That's the one, probably the only one, maybe the only one, over which we can exercise a lot of control. So I will be coming back to that. Then there's the CH4 methane. I didn't mention the N2O, that is nitrous oxide, is an important one. The O sub 3 is not the oxygen that we breathe, that's ozone. It's in the upper atmosphere. We don't have much control over that. Finally, on the right is CFC, an abbreviation for chlorofluorocarbons. This is the refrigerant that was used in air conditioning at first until we realized that it was a potent greenhouse gas, and some of this, maybe a lot of it, was escaping from air conditioners, was getting into the atmosphere, and was contributing in a major way to the greenhouse effect or the atmospheric effect. And by then the handwriting was on the wall. We knew that we didn't want to put any more greenhouse gases into the air than we had to, so the chlorofluorocarbons were then replaced by other refrigerants. There are still CFCs in the atmosphere, but they're slowly disappearing, and maybe in another 20 years or so they will be insignificant in importance. Let's go back to carbon dioxide here. Just one point that I want to make, and that is that carbon dioxide is increasing in a major way in the atmosphere. Measurements, regular measurements of carbon dioxide started, I believe, in Hawaii on Mount Mauna Loa in 1958. And I'm sure it wasn't clear initially just what was going on there, because you needed a few years of measurements to realize that carbon dioxide is increasing in concentration. And so the left part of the curve here was all they had at the time, but they could see it was increasing. And that was enough to justify continuing the measurements. And it's a very good thing they did, because the curve continued to climb. This curve ends, I believe, at the end of 2018 or thereabouts. Went on the computer a while back using the website that is down at the bottom of the screen. And I found that at that time, the most recent information was in July of 2020. The increase has continued beyond the curve, and it was 414 parts per million in July of 2020. And that is quite a bit above the roughly 310 parts per million that they measured at the start of this study. If you are looking at this talk, let's say later in 2021, you could go to the website that I have here, and you can update what is on the screen here. I would almost bet, and I don't bet very much, that the value you get from, let's say, February or March or April of 2021 will be above this 414 that I got. Now, because carbon dioxide is emitted by coal-fired power plants, it is emitted by automobiles, well, actually vehicles, I should say, probably including trucks, it is an anthropogenic effect. There are probably natural sources of carbon dioxide, volcanoes, for example, but it appears that the increase that we see here is largely a result of anthropogenic sources. Is the greenhouse effect good or bad? Is the atmospheric effect good or bad? And I think we would have to say that it is good. Proof of that, you can calculate using a numerical model, you can calculate what Earth's temperature would be if we did not have this atmospheric effect, or the greenhouse effect on this slide. And the average temperature of the Earth would be 6 degrees below 0 Fahrenheit. That's average. At the tropics, it would be warmer than that. At the poles, it would be colder than that. But -6 on average makes a lot of areas that are presently livable unlivable without the greenhouse effect. So you might say it's good. With the greenhouse effect now, the average temperature of the Earth is about 59 degrees Fahrenheit, 15 degrees centigrade, which is quite comfortable. There are still polar areas that are unlivable, but with the greenhouse effect, we have what we have, and there are a lot of habitable areas. The catch here is that we don't want too much of a good thing. We don't want to increase the greenhouse effect so that the 15 degrees centigrade average goes to 16, 17, 18, 19. That would make areas that are presently warm but tolerable, maybe too warm, hot, and intolerable. On the other hand, it would in fact open up some high latitude areas. It would have an effect on crops. Crops that grow in certain areas now with the climate that is there would not be growable there. They would have to be moved to another latitude where that temperature occurs with the enhanced atmospheric effect. These are among the effects that we're not getting into. There, I got off the track here. So if you put all of these together, the net effect of all of the 10 processes that we have now gone through, you get a curve, actually 3 curves, that you see over on the right. The GISS is the Goddard Institute for Space Studies. This CRT3 is the Hadley Center. It's an English group. The NCDC is the National Climate Data Center. There are some differences in these 3 plots, these 3 color-coded plots, but you can see that they're all showing pretty much the same thing. It's an irregular increase. True, in the first maybe 3 decades of the record, Earth's surface temperature was decreasing slightly. Then it increased sort of sharply over maybe the next 40 years or so. Dipped down a little bit in the 1940s, stabilized in the 1950s, and now it's been going up since about 1970 or so. And it's this final increase, which looks like a steady increase. We don't know. We don't have information beyond the 2020, but it looks like it's going to be a steady increase, and that is what is concerning people. Just one final word here before we get into the effects of climate change, the effect of climate change. Right now, if you look at the slope of that line for the final 50 years or so, you can see that it is 0.17, between 1/10 and 2/10 of a degree centigrade per decade, which would be like between 1/100th and 2/100ths of a degree per year. And you might say, well, that sounds insignificantly small. But again, what is insignificantly small over a year or two or three is cumulative. And when you start working with longer time scales, decades anyway, the temperature increase that will accumulate over that longer time scale can be significant. Up to this point, we have been talking about the causes of climate change, and recall that climate can change either in the form of warming or cooling, more precipitation, less precipitation. Now we're going to be talking about one effect of climate change. This slide shows a few more, but I'll just go through them in a sentence or two, and then we will focus on sea level rise. If we are thinking in terms of global warming in particular, climate can cool, of course, but for the list here, I've focused on effects of climate change in the form of warming. That could include over land, color-coded red. That could include longer summers, milder winters, could include droughts. We've certainly been hearing about forest fires recently. Glaciers and permafrost can melt, and that's the one that's going to be of interest to us here, because as the glaciers and the permafrost melts, that water runs into the ocean and sea level rises. That's one cause for sea level rise. Just as the air over land is warming, the oceans will also warm, and as a result of that, we hear about coral bleaching. There's Arctic sea ice loss. Ice shelves in Antarctica and maybe to a lesser extent Greenland will collapse. But as water warms, it expands, and as water expands, sea level rises. So whether we're talking about processes on land, like the glaciers and the permafrost melting, which raises sea level, or processes in the ocean, the warming or the increase in the water temperature, which expands sea level and raises water level, we've got two possibilities here for the rise in sea level. And that's the one that I want to concentrate on. We'll look a little bit at the past rise and fall in sea level, look at what's going on now, and then make some estimates regarding the future. The relationship between climate change and sea level is fairly straightforward. If climate change is in the form of warming, then we have less ice on land as the glaciers melt and sea level will rise. So warmer temperatures, higher sea level. If climate change is in the form of cooling, the glaciers will be allowed to form, and that will take water that had been in the ocean, deposited on land in the form of glaciers, and so as the glaciers grow, the ocean, which is providing that ice, in effect, will fall. So as continental ice increases, sea level decreases. As continental ice decreases, sea level comes up. There are many examples of ocean floor, shallow ocean floor, that used to be underwater but became exposed when sea level fell. The example I'm going to give is in the Bering Strait, which is that narrow waterway between the easternmost part of Russia, what is now Russia, Siberia, and the westernmost part of North America, which is Alaska. Now that's, I think, about 50 miles or so across, and the maximum water depth is 45 to 50 meters. When sea level was lower, and sea level did decrease by up to 125 meters, that was all exposed, as was the shallow ocean floor, what had been shallow ocean floor, both to the north and to the south. That provided the land bridge, which allowed people from Siberia to cross, move eastward into what would become Alaska. They were the Native Americans, and that's how we got our Native American population. This was happening roughly 20,000 years ago. Florida was also impacted big time by lower sea level. In the gold color here, you can see the Florida Peninsula as we know it today. The yellowish area that extends especially off to the west into the Gulf of Mexico, but maybe off North Florida, significant extension or expansion to the east into the Atlantic, shows you the land area that was exposed when sea level was lower, and presumably that was grasslands and palm trees and that sort of thing, just like large areas of Florida are today. Cuba was a little bit wider, a little bit broader. Often in the far left there, you can see the tip of the Yucatan Peninsula extending into the Gulf of Mexico. There was more exposed area there. And the Bahamas especially, which are surrounded by shallow banks, that was all the small islands, relatively small islands that we have today, were expanded in a major way by the exposed ocean floor. Currently, using information from Key West, which has been available since 1913, currently water level is rising by just under 2.5 millimeters per year. Now, millimeters are pretty darn small, and from year to year, this is another one of these cases where from year to year the effect is very slight, but the cumulative effect over decades and especially centuries can be substantial. So we get 2.5 millimeters per year, but for example, over my lifetime, and you can calculate for your lifetime, but over my lifetime, water level has come up about 15 centimeters or so. This increase that we see is the result of the adding of water, melting of glaciers, continental ice, and the expansion as the oceans warm. What controls sea level rise? Well, anything that controls climate change, that controls the warming or the cooling, will control sea level rise. So that would include solar output that we were talking about, volcanic activity, greenhouse gas emissions, and again, I want to take a little more time on this, even though this gets very iffy. The greenhouse gas emissions that will influence the atmospheric effect that we were talking about can only be estimated in a rough sort of way. Greenhouse gas emissions depend upon how many people there will be, so we need, first of all, an estimate of population in the coming decades. We have to be able to make economic forecasts, because even if we know how many people there are, we have to know if they are in countries with strong economies and they can go out and buy cars, or if the economies are weaker and these people have to get around on bicycles or on foot. We have to make economic forecasts. And even beyond that, if we know the number of people, we know they can buy cars, we have to know something about how fuel efficient these cars are. So we have to be able to predict or at least estimate the technological advances. And as you might imagine, this gets very, very iffy. And I put the et cetera down at the bottom there just to remind me that we went through 10 causes of climate change, 10 possible causes influencing sea level rise, and I've only gone through probably the most important 3 here. There are plots of where this will all end up, and it just depends upon the carbon emissions, the greenhouse gas concentrations that occur from here through the end of the century. We don't know which of these curves is going to be the one that pans out, so I just put all the curves up here and we just have to wait and see what happens. But if the greenhouse gas emissions are extreme, In other words, if we have a lot of people, if there are strong economies, they buy cars, and the technological advances are very poor, then we would have a lot of fuel inefficient cars. We would get a lot of greenhouse gases out of those emissions, and the climate would warm and sea level would rise correspondingly. And we can go down through the high, the intermediate high, all the way down to low, which would be a best case scenario, which within the context of sea level rise means that there wouldn't be that many people, and or the economies wouldn't be all that strong, and or there would be very fuel efficient cars, all of which would reduce the carbon emissions into the atmosphere. And to put numbers to these, at the one extreme, if the greenhouse gas emissions are extreme, we could have a sea level rise by the end of the 21st century of 2.5 meters. That's a worst case scenario. Maybe at the other extreme, if the emissions are low, we could have as little as about 0.3 of a meter rise in sea level. Maybe just as a working range, we should look at the sea level rise that's between the intermediate low and the intermediate high. And just as a number to work with or a number to remember, maybe somewhere between 1.5 meters or as little as 0.5 meters. Has sea level been high before? Yes, it has. You can see in the picture in the lower left there, the red area along the coast is the area that was inundated about 120,000 years ago when water levels were 8 to 10 meters higher than they are. MOA, which would be just off to the right of the picture in the lower right, we're shooting across the pond here toward the sand dune, and MOA would have been slightly underwater because the ridge, as we call it now, with Highway 1 just on the other side, that was the coast 120,000 years ago. So here at the Ed Center, we would have been in shallow water, MOA would have been in shallow water, and the beach would have been on the near side of the ridge. That would be the sand dune right at the coast. How high can sea level rise? Well, we've got, again, a worst case scenario here. Keeping in mind that 85% of Earth's fresh water is presently tied up in Antarctica and Greenland for the most part. If all of that melted, nobody's predicting that it will all melt, but just taking that as a worst case scenario, sea level would rise about 63 meters. That would inundate most of Florida. A large part of that 63 meters would come from the loss of Antarctic ice, and most of the rest from the loss of Greenland ice. And just for reference, if you go to Lakewood Park, and this is not our Lakewood Park here on the other side of US 1, but there's a Lakewood Park in the northern part of the state, and that is distinguished because it is the highest land in the state, 345 feet, 105 meters. Now, if water level with all the melting comes up 63 meters, this would still be about 40 meters above sea level, but Florida would be reduced to a relatively small island around Lakewood Park. And we would have left Florida, I guess. We wouldn't all crowd into Lakewood Park, but we would lose pretty much all of the state. How important is this? Well, I think I just touched on this, but I'll generalize and say that it depends on where you live. This picture taken along the west coast of Australia. I don't have for scale anything at the coast down at the bottom there, or maybe a house up on top. I don't have anything that would allow you to judge. Perhaps the size of the waves is helpful, but I think we would all agree that the height of this cliff means that anybody with a house up on top is not worried about sea level very much, and so it's not a big deal on the west coast of Australia. On the other hand, and much closer to home, this picture was taken just offshore of Hutchinson Island, and you can see that there's not much elevation along the coast in this part of Florida. So with a rise in sea level of 1 meter or 2, we would be losing a large part of Hutchinson Island. So I am at the end of the one effect that I wanted to talk about, and it's time to go back and give you a 60-second summary. We've been talking about climate, not weather. We've been talking about climate, and the emphasis has been on temperature and precipitation, and I think now you would agree the emphasis was definitely on temperature. Talked about the causes. There were extraterrestrial causes, the orbital factors, the Earth going around the sun and so forth. The conditions in the atmosphere, the haze, the dust, that sort of thing. The greenhouse gases were also included there. I've been keeping track of the natural and the anthropogenic breakdown. Some of these are occurring rapidly, which means coming and going over the course of a year. Some of them slowly. I've been using the term millennia, but it's actually many millennia to describe things like mountain building or plate tectonics. And then finally we got into sea level change, just the past few slides, and I made the point that the sea level is rising now, but at other times it has been significantly lower than it is now, and at other times it has been significantly higher. Presently at 2 to 3 millimeters per year, not much in a given year, but a big deal when it accumulates over enough time. And then finally, the estimates, which require some understanding of where population is going, where the economics is going, and where technology is going. The future estimates seem to say that by the end of the century, water levels will be anywhere from a half meter to 1.5 meters higher than they are now. And that is where I will stop.